introduction, and thanks for being here. I didn't expect the workshop to be so crowded, so I hope I'll be up to the task today. So, as Daniel was saying, this talk will not involve Janus, even though I'll probably use a Janus here and there just for the sake of some steps that I'll describe, just because I have it installed, it's easier for me to do. But the steps, the things that I'll explain here should be easy enough to apply to any kind of SIPP and WebRTC-based infrastructure, and I'll also try to explain why that is. And in particular, the presentation I'm going to make today is also not meant to be a complete, let's say, overview on everything that can be done in this specific field. It mostly focuses on our own experience as a team on this kind of tasks, because of course we also have had the need of doing something like this, whether it was on plain SIPP in the past or WebRTC right now. And so I'm going to share our experience on this and the way we tackled these things. So in case you feel there's anything missing and so on, please feel free to tell me during the presentation at the end and so on, so that we can make this as much a part of the conversation as the content of the presentation itself. And so let's go with the presentation. I mean, this is just a brief agenda of what I'll go through. I'll start with a brief introduction about what you can do to stress SIPP infrastructures right now, and this is one of the things you probably know much more about than me, so I'll go pretty fast on it, just to show you a couple of tools that you can use for the job and how they work so fast, and but more in particular to explain why this kind of approaches mostly don't work whenever you want to get to a WebRTC in the picture. So I'll try to explain why that is. So, and I also try to explain different ways you can try and cope with this in the WebRTC way. And as Daniel said, yeah, this is my second time in Kamailio, so you may remember me from last year. There is a recording of the presentation I made on Janus. I love this picture, so I put it everywhere I go. I hope you won't mind. And then just a couple of words on us. I'm one of the co-founders of Meetecho. So we were born as an academic spin-off a few years ago. So all the members of Meetecho are either PhD students or people who got their PhD degree with a professor, with Simon Pietro Romano. So at the time we worked a lot on research activities within the university, a lot on multimedia applications. Eventually we came up with something that we thought could be called a product, and so that's how Meetecho was born. And since then, we basically try to widen the scope to real-time multimedia applications in general. So not just web conferencing as in the beginning, but pretty much everything that has video or audio or text or anything real-time going one way to the other. And of course, for this, WebRTC proves to be a great opportunity for us, which is also the framework in which Janus was born when we decided to start tackling it. And of course, we do all the kind of activities that you can expect from a small company like us. This is where we live and work, and actually I think this picture contains both the office and my home somewhere. I'm not sure where exactly. So I live around here, the office is around here, so a nice place to be if you want. And so starting with the actual content of the presentation, of course, whenever we talk about load testing of SIPP infrastructures, we actually don't mention a single thing. So it can actually mean different things. So in particular, we may be interested in how many SIPP sessions, for instance, our service can handle, but this also doesn't tell us everything, because it may be in terms of how many calls per second, how many concurrent calls, is the quality good enough? So when numbers increase, does that number change? Of course, when media is involved, how can I involve media in the picture when doing load testing? And so when probably I will not have real media that is actually being originated by, I have to simulate it somehow and things like this. And so, as you can expect, this is quite a complex task to take into account, considering, of course, that programmability and customizability are important requirements when you do something like this, because one thing is to just have a tool that just generates a lot of calls per second and stuff like this, but not all applications are the same. So the call flow may be different. So it may be different from a simple invite to 100OK hack and buy after a while. You may involve different steps. There may be interaction with the user simulated via DJMF tones and stuff like this. Different applications have, of course, different scenarios that you have to tackle. You may also want to simulate and orchestrate different topologies and things like this. So all things that are to be taken into account. You may want to have custom headers, fields, and stuff like this that may need to be different in terms of different people accessing the service, and not just the same user that you replicate 100 of times and stuff like this. So you get the point. And luckily enough, in the SIPP world, there are several tools that can be actually used for the purpose. One of which, and the one that I'm going to talk a bit today, is SIPP, which is probably the de facto standard when it comes to this. It's an open source component that allows you to design complex scenarios and then generate test campaigns for this, something that we used in the past as well. There's Seagull, which is also another popular open source multi-platform, in this case, traffic generator, and there are others, so you'll find many more if you look around. Most of them are also not open source, they may be proprietary, there may be people charging for the service, which is of course normal, but you get the picture. There are a lot of ways that you can do these kind of things. And as I was saying, I will focus a bit on SIPP, mostly because it's the one that we as a company were more familiar with. It's the tool that we used when we needed something like this in the past. And as I was saying, we think it's probably the de facto standard tool for generating SIP traffic, whether this involves media or not, because I chatted with many people in the past about this, and they almost always use this. And it looks like it's still being used quite a lot in the testing of SIP-based infrastructures. And in case you don't know how it works, it basically makes use of XML files to design the testing campaign. So as we'll see in a minute, because I'll show a simple snippet of how this works, you basically create an XML file with the expected scenario that you are trying to explain. So in terms of the sequence of messages, in terms of maybe custom fields that you may want to add, static or dynamic headers, stuff that may need to be dynamic in terms of what you pass when you execute it, and so on. And the interesting thing is that, of course, if you want to start quickly, there are CPP also comes from some precompiled scenarios. So if you just need a simple user agent client or a simple user agent server, there are ways to spawn them quite easily without you having to worry too much about designing an XML file yourself. But of course, if we want to do some more complex things and so on, being able to understand how these XML files work and being able to actually modify them somehow actually helps in making things more complicated than it is by default. And there are also options to customize the session, as I was saying, even in real time. So for instance, you started with, let's say, a rate of 50 calls per second or something like this. There are ways to increase this dynamically from the simple CPP console application, so that you can actually change a bit the dynamics of the scenario that you are trying to reproduce. And this is an important aspect. This is not only related to signaling, because of course XML files are mostly focused on signaling itself, but you can also involve media in the process, which means that you can generate a SIP code that actually starts exchanging RTP media with the service that you're trying to test, which means that you can have, in particular with respect to CPP, you can have a pickup file, so a file that you captured before with TCP dump, Wireshark, or whatever, available, and you may want to just replay the contents of this pre-captured file so that it is actually used as the RTP source for the call itself, which is actually kind of interesting, because it allows you to actually do a call with media with basically really close to none overhead in terms of CPU consumption, because all the tool is doing is basically just accessing a pre-recorded file and then just shooting the RTP packet at the exact moment and so on, of course using the ports that were used for the negotiation and things like this. And when you actually start then CPP, it looks pretty much like this. So you have an overview of the scenario that you described in the XML file, and this simple sequence diagram explains, would differ, of course, depending on how you actually designed the XML file yourself. It gives you an overview of the current configuration of what has happened and so on. And of course, it also gives you an overview of whatever is happening at that specific moment. So how many messages of a specific step in the sequence diagram, the sequence steps that you described have been taken care of, what is going to change, and so on. And if we want to have a look at how the XML looks like in principle, we can summarize it like this. So this is a simple example of how you can design a very simple user agent client with CPP. So as you can see, you have a scenario element that you can then just populate with the different steps that need to be part of the of the testing campaign. And so we may want to start with a simple, we start with a message. In this case, I'm just snipping it for visibility reasons, but I show you the full example later. We may start with an invite, and then we'll say that we are going to expect either a 100 and 180 or a 200 back. So we are okay in getting provisional responses and so on. At the end, we expect the 200 to actually in reply to our own invite. After that, we plan to send an ACK, of course, and then we may pause for some time to say this call is going to last, let's say, 20, 30 seconds, depending on the scenario that you are going to exemplify. And after that, in this case, after 30 seconds, we are going to send a bye message, and we are going to expect the 200 back. So if when we do this campaign, everything works as expected, then the SIPP tool will basically show us all the dynamics of this specific call scenario in the interface and so on. And if we explode that first part, so for instance, the invite part, this is how we may actually design the complete message that we are going to send as part of this testing campaign. So in this case, you see there are a lot of parts that are actually dynamic. So the ones that you see in the square brackets are all parts that actually the SIPP tool is going to inject dynamically for each call. And some of these may actually be driven by something that you provide yourself, either via command line or some way else. Others may actually be generated dynamically by the tool. So for instance, the call ID may be something that the tool may introduce dynamically to use a different one for each call and stuff like this. And in this case, you can see that in this example, I added a custom header that needs to be part of all the invites, because this may be part of the service that I'm testing. I'm passing, for instance, a custom subject and so on. I'm specifying in the SDP that I want to negotiate ALO, so all the parts that are related to the dynamic negotiation, of course, with the media port that is going to be dynamic, so to allow the SIPP tool to negotiate stuff and handle RTP on its own. And that's pretty much it. So you'll see there are several other fields that you can configure, which is kind of cool. And of course, how does media get into this at this point? As you can expect, the ability to send or not send media is actually part of the XML scenario itself, because the XML scenario describes exactly what the SIPP tool needs to do during all the code that we are going to replicate, which means that it makes sense to have an additional part in the XML file to address exactly this. And in fact, it's pretty straightforward. We typically just use an XML snippet that looks like this, where you point to the pickup file that you want to replicate, and you have to match it with a pause element that basically says pause for this amount of time, which is basically the length of the pickup file, which to make a simple example. So in this case, I'm introducing a simple allo pre-recorded RTP snippet that comes shipped with the SIPP tools itself, which lasts about 8 seconds if you listen to it, which means that I can just inject these here, add a pause there, and so on. If I need more, I can generate my own traffic and stuff like this. And if we have a quick look at how a complete XML file looks like, this is the one that I'm going to use in a minute in a very simple demo that we can use to show how it works. And as you can see, this is exactly the same that I've just displayed in the slide. So you can see exactly the same custom header, some additional information, a custom subject, and so on. And this is the complete scenario. So again, I'm going to expect either a provisional response is fine. I'm not going to care much about it. The important thing is that I receive a 200. Then I'll send an ACK back. Again, I'm providing the whole content of the ACK message that I'm going to send back. I'll pre-record some data for a little while, and then I'll send a bye after a few seconds. So if we want to see how this all works, we can just, let's say, spawn an asterisk here just as the service that we want to stress in this case. And then I can just, you can just generate the traffic using this CPP tool that we've seen so far. And so if we look at the SIPP can just be launched via the command line. So I'm going to do exactly that, which is I'm going to use to run as a sudo, because if you want to replay the RTP stream, you need to have access to some stuff that the normal user will not be able to do. And in general, I'm telling the CPP tool to use this XML file as a scenario for the stuff that we want to do. I'm saying that I'm going just to generate a couple of calls per second. There's going to be a limit of 100 concurrent calls at the same time, but in general, I want to test 300 calls in general, basically. And then I have some additional information like the duration of the call, some stuff related to the ports, and most importantly, the servers that I want to call. And in this case, I'm going to call the echo test extension on asterisk on the IP of my machine. So let's see if this works right now. So right now, you can see that the tool has started generating the calls as I was saying. So you can see that about 2 calls per second are being generated, and of course, some are still in the pause part. And so you'll see that in a minute, we'll start seeing some buys originated, because I have a couple of replays that to make the call basically last about 15 seconds. And after that, as soon as the first call ends, you can see that some of the calls are being hanged up as part of this, which is all reflected, of course, in the asterisk console, which shows you that I'm actually handling all these calls and exchanging media with them as a consequence of that. And as I was saying, I can also increase a bit the rate to have, let's say, more calls being sent at the same time and stuff like this. So in this case, I'm sending 4 calls a second instead of 2 and so on, all things that I can change dynamically, basically. So as you see, nothing complicated in principle, but this kind of works. So coming back to the slides, of course, as you can understand, CPP in principle is very powerful, but designing those XML files can be a problem, because it can be problematic to design scenarios that are complex enough by hand and so on. And fortunately, there are a couple of tools that will not go through, but I'll just summarize here for your convenience. For instance, there's a tool called SIPP Pickup by Mojolingo that allows you to basically design these diagrams, these campaigns in a more user-friendly way, and that gets translated in turn in the XML files that you end up using with CPP eventually. But it makes things much easier, of course. And of course, CP Pickup and other tools as well also provide some web front ends to make things easier, also in terms of how to handle the amount of information that you get out of all these testing campaigns. And for instance, the Mojolingo authors have a tool that allows you to basically summarize all the results of a testing campaign, so that you can then evaluate them for your own needs and stuff like this. So all of this introduction for what? To basically say that most of the stuff that I've talked so far does not apply that easily to WebRTC, and we'll see why in a second. So you may have seen this very ugly slide before, because this is another of the slides that I always use, even though I should probably replace it because it's really ugly. But in principle, it makes you understand that in principle, WebRTC kind of looks like SIPP. So the WebRTC typical architecture looks like a bit the SIPP trapezoid, if you like, where you have 2 people exchanging information in terms of signaling and negotiation with, in this case, a web server, and then eventually exchange media peer-to-peer. The problem is that the signaling that you see over there is not, let's say, mandatory. So there is no way to actually know in advance which signaling is going to be used with some specific WebRTC services or not. And so you cannot assume that the signaling there will be SIPP, for instance. Actually, most of the services, it will be something else, which means that if you want this WebRTC user to talk with the SIPP endpoint on the other hand, who doesn't talk all the stuff that WebRTC standards introduced, you'll have to put something in the middle to take care of that. So something that either takes care of the signaling, and at the very least, for instance, it needs to expose a WebSocket interface if you're still using SIPP, for instance. So if you're still using, for instance, with Kamailio, you can use SIPP over WebSockets. In that case, you have to make sure that the SIPP over WebSockets, for instance, gets to a SIPP that is either over UDP or TCP or something like this on the other end, or you have to take care of a whole signaling translation mechanism in principle, and even possibly SDP adaptation, because again, the SDP is what will end up in the establishment of a media connection, and the SDP WebRTC users will use is actually going to have a lot of information that regular SIPP users will not be able to use at all. So stuff that may be related to ICE, DTLS, SRTP, and stuff like this. And this is because, as I was mentioning, WebRTC added a lot of stuff to the plain SIP-based infrastructure. So again, I was saying that the signaling is not standardized, even though there is, let's say, a state machine that needs to be followed in order to keep things working on the WebRTC. And SDP is still used, even though it's something like SDP on steroids, so you need to take care of that. And then a lot of things that you need to implement that may not be part of a SIP infrastructure, something that typically drives some people crazy. But likely for you, there's people who have taken care of this on your behalf. So the problem with load testing is that, first of all, simulating users is not as trivial as we've seen with CPP, for instance. And that's because a WebRTC client is typically, even if we just assume a web page or something, they are not just simply web users, because again, one part is of course the web interface, so interacting HTML5, JavaScript, and things like this. But then there is also a whole lot of stuff that you cannot do with simple web replays and things like this. So all the WebRTC part is really dynamic and is not, strictly speaking, a web application if you think about it. And at the same time, they are not regular SIP clients either, for the reasons that we've seen before. So there is a whole lot protocols, a whole additional lot of protocols that you need to take into account, which is actually kind of problematic to simulate and to handle. Which means that CPP, for instance, would not help you simulate and stress a WebRTC infrastructure, because although it might work with the signaling part somehow, so if you take care, for instance, of proxying the WebSocket stuff and things like this your own way, but definitely you cannot use pickup files to just replay media as you did with regular SIP infrastructure. And for a simple reason, I mean, WebRTC is very dynamic in the terms of how you exchange, how you establish a media connection, which does not couple well with simple replaying of media, because you need to take care of all the ICE process in order to establish a working communication between two endpoints, and that's very dynamic, as you can expect. Something that you cannot just replay, because there is going also to be authentication involved and so on. Even if you coped with the ICE stuff, then you would need to take care of DTLS, which again is something that you establish on the fly, not something that you can replay. Of course, because replays is something, one of the things that DTLS and SRTP are trying to prevent in the first place. And in principle, as you can imagine, WebRTC is simply too dynamic to just replay traffic and so on, and so CPP is not a good option in this case. And while there are some tools that allow you to generate a lot of HTTPS or WebSockets traffic, like JMeter, Siege, HTTPerf, and things like this, as we were saying, they are not fit for WebRTC because they only would handle the HTTP part. So you can download the same page 10,000 times, but it really doesn't suit the purpose, because what you want to do is not how many people can actually just open the page and display the HTML content, but how many of those users will be able to establish a working WebRTC connectivity with it, something that these tools don't provide. And while you think that maybe Phantom.js could help you with that, because it allows you to simulate all and automate, most importantly, all the JavaScript parts, that's not enough either, because so far Phantom.js doesn't support WebRTC yet. So it does allow you to do some WebRTC, some JavaScript dynamic stuff, but it doesn't allow you to create WebRTC peer connection and things like this. So you may be wondering at this point, are we completely lost, or is there something that we can do? And of course, I'm just halfway through my presentation, so I hope I'll have some solutions for you. One of those being what in Napoli we might call the pane puparoli way. Pane puparoli means basically just a slice of bread with some pepper on it, which means and in Napolitan it means something that is really trivial and easy, but at least gives you a bit of flavor, basically. So the easiest way that you can do is to basically just open multiple tabs, because while, as we were saying, WebRTC users are not regular SIP users, on another aspect, they're actually more fit than SIP users in order to do some testing and so on, because they are basically web applications, and web applications are scriptable. You can do a lot more things if you mess with the JavaScript and so on, which is actually kind of a nice thing. especially because it's much easier in this case to open a lot of pages exposing your own soft phone interface than opening, let's say, a ton of soft phones at the same time, which is actually kind of cool. And that's possible, of course, because JavaScript allows you for doing something like this. Of course, this is just the pane popolari way, meaning it's the really easy and quick way to get something working. So to generate, let's say, 20, 30 calls at the same time and see how it works. But of course, there are severe limitations because let's say, there may be a limit on how many tabs you open yourself, how many browsers you can open on a single machine before it melts down. There may be local resources that are exhausted, or even just, if you think about it, the browser connection limits may be exhausted because, for instance, in all the browsers, there's a limit on how many HTTP connections you can send towards the same web server. So if you are using, for instance, long polling in your application, and then you open 10, 20 tabs at the same time, those long polls will keep the HTTP connections busy. The regular requests will not be able to get through to the same web server. The application will not work, basically. So all things that need to be taken into account. And of course, for resources, there may be some things that you can do to prevent the machines from overusing your resources. So for instance, you may use fake devices rather than accessing the actual microphone, webcam, or things like this. And other things that you can do to increase the behavior and so on. You can get friends to help and so on, but how many people can you involve into a test like this? For instance, it's 5 of us in the Meetecho office. I may involve all of them for a test that we can do, but at this point, all of our laptops are busy just doing that. There's nothing else we can do. There is to be some way that we can use the same approach in a more efficient way, let's say, rather than just let's say, do this thing and then do something else. And so, as you may have understood, this is actually very silly and very naive, but it's actually a good starting point to do something more efficient, as we'll see, especially if you find a way to automate and remotize all of this, which is exactly what I'm going to talk right now, which is the so-called Selenium HQ, which is a tool that basically allows you to do remote browser automation, which means what? It basically means that considering that web applications are scriptable by definition, and most importantly, they can also collect statistics, which is also important, for instance, for the question that one person in the audience made before to Giacomo during his presentation. Even if you have a peer-to-peer call, you can still collect statistics on both sides of the communication using JavaScript, for instance, and pipe this information towards a component that can digest and use them. So, for instance, Homer in this case, which makes these endpoints, so even the soft phone, if you're just doing a SIPP-based application over WebRTC, much more powerful than a simple and configurable than a simple SIPP soft phone, because you can do pretty much everything that you need in order to automate some of the aspects and do some cool things. And basically, Selenium allows you to spawn remotely controlled browser instances and then open a specific web page and then drive whatever needs to happen also to simulate JavaScript communication, dynamic user input, and stuff like this. Which is kind of interesting because any of these scenarios, so any of these controllable browser instances that you can do, can actually be implemented in different programming languages. So Selenium provides binding for a few of them. In a minute, I'm going to show you how I can actually do something like this with JavaScript, which is kind of cool. Of course, this needs a hook with the nature of specific browsers, and Selenium provides web drivers for different browsers. So you'll have a driver for Firefox, a driver for Chrome, and things like this. I was mentioning fake devices before because especially if you're going to do this browser automation not on your own machine, but on a server somewhere, there may be no webcam to actually access, or you may not want it to have access to any webcam and so on. Which means that fake devices can greatly help you with this task. And most importantly, considering that, in case you don't know, WebRTC also asks you for the permission anytime you access a specific device, a microphone, a webcam, and so on. If we want to avoid that step, because it basically hinders our ability to automate some of these things, there are also flags that you can set in these browsers to actually prevent that part. So you assume that the permission has been accepted and you move on, so without having to worry about that step. There are also tricks that allow you to start these browsers in a headless way. So, for instance, without actually presenting a browser instance on the machine that you are going to simulate. In this case, I'm not going to use them. So in the example that I'll show you in a minute, I'll show you how I can spawn a browser and to do something that I want so that you'll be able to see exactly what happens. But of course, this takes resources because it uses the graphic card and so on. Some servers may actually not even have a graphic card. They may be completely headless. So you may want to use stuff like the virtual frame buffers and so on to actually get rid of that part, which would make also the simulation much easier to handle. And in the future, maybe, who knows, the headless Chromium stuff that has been added recently may also help in that sense. And this is actually a quite cool and powerful feature because there's a popular company that does RTC-based testing that is called TestRTC. And of course, they do a lot of stuff, additional stuff, but Selenium is actually part of the foundation of what they do. So just to make you understand, it's actually a quite powerful thing. So just to give you an idea of how you can actually design a scenario to do something, I'm showing you here a simple example of a, as you can see, very short Node.js application that shows you how you can open a web page, decide how the simulated user must behave, and then do something. So just to give you an idea, I'm going to use the Janus SIPP test demo. So this is just, I'm going to show you first the demo used in an interactive way. So I'm going to insert some data into it and so on. And then I'll show you how I can automate all these steps in a simple scripting language, which in this case is JavaScript, to basically simulate the behavior in a programmatic way. So let me just start Janus in a second. It should be already up and running. So this is the SIPP gateway demo page. Let me start asterisk again, because that's who I'm going to talk to. So as the first thing, whenever you load the page, you have to press the start button. So this is something that I'm going to do manually. Then, as you would expect of any kind of demo, so also JS SIPP demos would work pretty much the same way. For instance, you have to insert some information. I'm going to insert this Janus user, which is one of the registered users on this machine. Let me check the IP of the machine here, just a second. If I can find the mouse, okay. Here it is. Okay. This is my identity right now in the platform. I'm going to use my password. Then I have to choose which registration approach I'm going to use. So this is something else that needs to be part, of course, of the user interaction. Just for the sake of simplicity, I'm going to use the plain secret. Another pop-up appears. I need to take these into account if I want to automate this process. Then I just register. I'm ready to do a call. Now I can just call, for instance, the echo test as I was doing before with SIPP. Call, allow, and we can see that I'm just now in the call and so on. After some time, I may decide to just hang up the call, which means pressing that specific button, and this scenario ends. So as you can see, there are some things that I need to do in order to simulate all of these, which is exactly what this scenario here does. So the first thing it says, open the Selenium WebDriver, do it for Chrome, use a fake device, so I'm not going to use a real webcam, I use a real microphone and so on. Don't ask me for any permission, that's that flag over there. Then I'm going to say, open this web page over here, which is the SIPP test demo, and then do a little steps in sequence. So press the start button, insert this value in the username part, insert this value in the password part, click that part which was the drop-down menu to choose which kind of secret you want. Make sure that you address that pop-up that I was going to show. Press register, wait a bit, insert this URL in the period that I'm going to call, press click, wait 10 seconds, and then press that same button again to hang up the call. So as you see, really easy, but also something that you need to take into account depending on how your application works. And now we are going to see it running to see if it's actually working exactly as we expected. And in particular, I'm going to use, let me see if I can show you this in a more easy way. I'm going to use a slightly modified version of this with some additional slip in it, because normally all those tests would be very fast because it would be all automated. I'm going to wait, let's say, a second anytime I do something so that you can see that it's actually doing something in, I don't know, an automated way without having me doing anything on its behalf. And so I can just do node test1.js, and we should see, oops, sorry, I forgot to start the Selenium driver. Let's just a second. Actually, it's another issue. Just give me a second. Okay. This quote stuff that I actually forgot to fix. Yeah, it's very dangerous. And it's actually kind of a spoiler alert. Part of this will also be in the dangerous demo that I'm not going to say more. So I better hope it works, because otherwise I'll have to go home tomorrow.
Lorenzo, I have a bunch of double quotes if you're missing more.
No, I'm okay. So I should be done. Okay, I'll have to probably fix another one as well, but that should be it. So I can start it. We should see a browser that has appeared, of course, in the wrong window, which is this one. It has already started doing some things on its own, so writing the name, pressing the button. Of course, it's called the DNS error for some reason, which is probably related to the address I used. Try again to see if it was temporary. I mean, it's not working right now, but as you can expect, in general, this would eventually result in a SIPP code. So in this case, it's probably related to some aspect related to the network here, but you get the idea. If that register had succeeded, I would have ended up into the call part that would have resulted into the button to call, and eventually in a call generated via the WebRTC stack of the browser. So that's basically how it would have worked. Maybe later I can try and figure out why. Yeah, it shouldn't be the issue though. So just let me modify the demo in a second to see if using a different one works. So just let's put the address over here. So also the right address here. So again, wrong monitor. Okay, it did work. So I am an idiot. So okay, then. But then this, you can see that I wasn't lying to you. Now it really did work. You can probably hear the stuff, the demo working, and this was only lasting 10 seconds. So the echo test was playing something. After 10 seconds, we hang up and like this. Of course, this is only interesting if we can automate it somehow. And so let's see, just for fun, if we can just do it. First of all, let me check if I have the same double quote kind of thing here. And probably, no, the address shouldn't be an issue because it's dynamic in this part of the demo, but so this is a slightly more complicated version of exactly the same thing, because as you can see, the way that we generate to interact with the driver is exactly the same. What we are doing is just, let's say, spicing it a bit. So I added some command line arguments by which I can specify a rate, a call limit, a max call. So pretty much the same thing that we did with SIPP in a very basic way. I have some defaults in here just to do some kind of cool things. But the idea here is to use this Node.js application to then generate more than just a single browser instance to do that call in a way that is compliant with the arguments that I put in there. So let's see if it actually works, even though all the screens will probably appear in the wrong place, which is my own screen, but I'll try to move them here.
You still have local host?
Yeah, no, in the... No, in here it's dynamic, so it's Janus SIPP user. Sorry? No, that local loss that you see here is just the default that I'm not going to care because I'm going to overwrite it with the command line argument. So, and then apart from this, I'm going to use localhost just to connect to the web page, I think, but not much more than that. So it should work, but let's see if I'm an idiot again. So let me see. Okay, just a second. I'm going to replace the localhost here with the right IP address. So I tried to make it look like a really stupid version of SIPP, so using pretty much the same arguments, like the argument to specify the concurrent calls, the limit number, the maximum number of calls, the duration, and things like this. I'm trying to do pretty much the same thing. So call the echo test on asterisk using, in this case, 1 call per second, the limit of max calls at the same time, a top of 10 calls in general, and each call is going to last 10 seconds. So we can just try to start this. Then you can see that there are some things happening in here, and that's because I'm going to I'm spawning all these instances over there. Now you see a lot of noise because I have 5 browsers basically doing the same thing in an automated way. And eventually you'll see this application hanging up, which is an example of what is happening in all of these screens in here. So you get the idea. It's actually quite powerful. So let me stop this because otherwise I'm going to to get crazy with all these voices in my head, which I already hear from time to time. And then basically, as you can see, it's actually quite powerful, but the problem with this is that even though it's actually kind of cool that there are tools that help you automate it and orchestrate a lot of browser instances, I'm not going to delve into this because it's not my field. Another guy in our team is actually very expert on this. But this is actually something that we've used a lot in the past also for some performance evaluations of our own gateway, and these are some graphics related to how the SIPP plugin worked, for instance. So we generated a lot of calls using Selenium and try and figure out how Janus would handle these calls in terms of CPU performance, memory load, bandwidth, and so on, which was kind of cool, and also to do some cross-references to remote and local mixing and things like this. The problem with this is that you're still, even with all the optimizations that you can do, fake devices, frame buffer, and things like this, Selenium is still kind of heavy if you think about it, because a single machine can only handle and open and so many browsers without actually starting to suffer from this. And this is also because all the actual media interaction is actually being done with actual encoding and so on. So you're actually replicating a real endpoint in this, which is actually kind of heavy if you're doing video, for instance, or stuff like this. There are only so many browsers that you can open on a single server. How many depends on the server that you have, of course. And if you don't have that many servers, then your scalability actually is limited. So for instance, it was our own case, because at the time we could only generate about 300 and something endpoints at the same time before we actually ended up of servers to use for this. And so we actually couldn't get a complete evaluation of Janus, for instance, for this specific use case. And in this case, then, if the user interface is only of a relevant nature, because sometimes you actually want to test everything, so including how your own application works in this sense, but are more interested in just testing the peer connections, then maybe a native tool can actually help, can actually do it better. So something that only implements peer connection and then leaves all the details about signaling and negotiation up to you, basically. So something that, again, should be controllable and programmable. So in principle, something like CPP, but for WebRTC, let's say, something like this. And something that, of course, should be able to send and receive media as well, so that you can evaluate things on your own in terms of quality of service and stuff like that. And while there are some tools out there, most of them are specific to target applications. So for instance, you may know the Jitsi Hammer is a really good tool that the Jitsi team implemented to stress test their own platform in order to evaluate whether it works fine or not under some numbers. But unfortunately, it's really specific to the specific application that they have. And in principle, though, the Chrome WebRTC stack, if you take it as a library, could be used for something like this. So you could implement your own general purpose application that uses the library pretty much as the browser does, and in order to do something like this. When we tried to look into this some time ago, we didn't find any, so we implemented one on our own that doesn't use the Google WebRTC stack, but we basically extracted the Janus WebRTC core and inserted it into a client-side application instead, which we call Jattack just because it was a kind of a nice mix between Jattack, that means I attack in French, and also because it gave the idea of Janus attack, because at the beginning we wanted to use this as a stress testing tool for our own platform. And it does exactly what we needed. So basically it allows you to generate a lot of peer connections by using a logic that is not within Jattack itself, but is part of an external controller. So the idea is that this tool can generate and receive a lot of peer connections at the same time. If you attach an RTP source that is external, so we don't generate RTP or media ourselves in our own, it can use this as the media that you inject in the peer connection, and then you get live events on everything so that you can monitor whatever happens. As I was saying, it was originally conceived for Janus, but considering that the signaling part is completely orthogonal to Jattack itself, it means that you can actually use it with other services as well, which means it could be used, for instance, to test other WebRTC services that are WebRTC based, and maybe your controller talks SIPP in order to handle all of this. And if you're interested in learning more, because of course I will not go too much into the details, there is a presentation that we made in Chicago last fall that describes all of this. And from an architectural perspective, it's kind of simple. So it's basically a decoupled version of CPP, if you will, because if we think that Janus is the service that we want to stress, and we have Jattack here that is able to generate a lot of pre-connections, all we need to have is some kind of a controller application, so something that is even scriptable, or a Node.js application, a Java application, or whatever, that basically tells Jattack what to do. So in this case, it would be, in the case of Janus, it would create all the sessions and the handles on the Janus side. It would negotiate all the SDP stuff back and forth, and then it would make sure that the SDPs, it would get an SDP from Jattack, use it to contact Janus. Janus would send an SDP back. It would send the SDP back to Jattack, so that eventually the communication is done here. And if it involves more components, the controller can take care of them all, basically. And this is the way it works when you have a media generator. So as I was saying, Jattack doesn't generate any media on its own, but you may have a controller that says, hey, spawn this video and RTP stream that I'm going to use for all the calls. It sends it via RTP, and then everything that is sent here is going to be injected in the WebRTC streams as well. So really, really lightweight for the needs that we had. And of course, this means that it's much more complicated than Selenium, because with Selenium, you could just take exactly the same, the web page that you use, for instance, in production, or in the case that I've shown a demo, just script something to make some behavior automatic, and then you'd be done. So there was nothing else that you needed to do. The application would take care of all the application and signaling logic. In this case, all the signaling, so the fact that you talk to a specific server to authenticate, to exchange media, to set up a WebRTC peer connection, and so on, you need to implement it yourself, of course, which means it's less trivial. But if you're interested in just the media part and stuff like this, it's actually much lighter, because, of course, you only need to take care of the signaling of taking care of some WebSockets connection and so on, which means that a single machine can simulate many more users than a single Selenium with some browsers on it can actually generate, which is actually kind of cool. And again, of course, most of the burden is designed on the controller, because you need to take care of the Jattack instances, implementing the signaling and stuff like this. But the cool thing about this is that, considering that the controller is completely separated by Jattack, you can implement it in anything you want. So if you wanted to implement in Python, you can do that. I don't know Python, so that's cool. This is a simple example of how you could implement a very simple SIPP calling scenario with Jattack. So you would just say, create a session for me, generate an offer. OK, this is the offer. These are the candidates and other events. I use this information in a SIPP invite that I send to a SIPP proxy. I get an SDP back. And of course, the proxy may involve a WebRTC gateway, because this is a WebRTC connection. I get an SDP back, I pass it to Jattack. Jattack will end up establishing the WebRTC communication with the WebRTC gateway. I get a working call. I repeat this n times, 2 per n times, and so on, depending on what I need to do. I basically replicated a scenario that can grow. So as you can see, quite simple from a conceptual part. And then, unfortunately, all of this that I've really explained in a GIF is actually not open source, at least not now, for a couple of reasons. One of those is that actually Jattack could even be seen as, considering that it's quite general purpose, almost a WebRTC denial of service tool. So, because it's really easy to just hammer the same server with a lot of stuff. I mean, it's probably a lame reason, but it's not really complete as of now. We need to wait a bit before we do that. But exactly the same concept that I've explained so far. So all this kind of sequence diagram, all these concepts that I've explained here, and so on and so forth, actually apply to any kind of native implementation and so on. And so as we were saying, you could implement exactly something really similar or pretty much the same using the Google WebRTC stack as the library to handle the WebRTC communication, which is something that a couple of projects have tried to do so far. So at least a couple that I know of. These two projects over here, Node WebRTC and WebRTC Native, are projects that try to bring the WebRTC stack within Node.js. So Node.js is something that you can control and program yourself and so on. And so having the ability to do something like this within a Node.js kind of framework would allow you to generate a lot of scenarios in a very simple way and then leverage the Chrome WebRTC stack to handle all the media stuff and then follow exactly the same steps that I've described so far. And in principle, they look like they are good candidates for the job. I haven't dealt with them enough and so on, but from the conversations that I've seen on the GitHub project and some Stack Overflow questions, it looked like they are not ready yet, but it looks like they are really on the good path. So if I were you, I'd monitor these two projects to see how they actually perform and so on. And as I was saying, ideally, once they are available, you can reuse exactly the same logic that we've used for our own tests in Jattack, also for your own scenarios like this. And just to conclude my presentation, and then I'm done, one more thing that you could actually do, even though this isn't something that I have a demo for or something that I can demonstrate easily, why not reuse some of the servers instead to simulate all the WebRTC part as a client? Because if you think about it, all those servers, Asterisk, FreeSwitch, RTC Engine, Janus, or whatever, any kind of service that is WebRTC enabled, all have a WebRTC stack ready. So they can already negotiate WebRTC sessions with a WebRTC related endpoint. So why not use those to stress other servers instead? So all you would need to do is having some kind of, again, a controller that can orchestrate all these servers to be used instead as puppets to generate a lot of traffic to then bridge the signaling towards a completely different service and then have them exchange media with each other. So as a very simple instance, I could use the Asterisk Manager interface or something more modern than that, because I'm really behind that in this case, to generate calls on Asterisk number 1, for instance. I get the WebRTC SDP. I use that SDP to call a completely other service, maybe with another protocol or still via SIPP. I get the WebRTC answer. I send it back to Asterisk. So pretty much the same concept that we had with Jattack, for instance. We repeat it 10 times, maybe involving other services as our own fake clients and so on. This should result in all media channels that we can exchange with actual media being exchanged between each other, because both of them will actually do something meaningful. And of course, this is less flexible and probably less straightforward, but in principle, especially if you're quite familiar with any of these platforms above, and so you know how to orchestrate these in an easy way and in a straightforward way, this could be a good knife in your belt to actually do something cool in that direction. So I think that's all. So if you have any question, if you have any insult for me in particular, considering the broken demos and so on, I'm all ears. Thank you for listening.
Thank you. Questions, but only if you can ask 2 per second. Okay, so because I'm also curious, I haven't gone much into stress testing with WebRTC. Where you see like the bottlenecks so far, it's like this encryption, decryption, or still the negotiation of the session, where what you try to test in most of the cases is like the parameters of the communication or the encryption, or where the most of the issues are exposed by the new browser or by new releases of applications.
Yeah, in principle, let's say there are different aspects that some scenarios, different aspects and whose impact is important in different scenarios, because sometimes you may have transcoding involved, sometimes transcoding may not be involved, and so on. And so that also drives a lot the shift on how many people I can handle, how many sessions I can control at the same time, and so on with respect to this. But most of the aims of our own tests in that direction have always been of how many connections I can handle at the same time. So for instance, with respect to Janus, we almost never do transcoding apart in a couple of plugins. And so in that case, we were mostly interested in how many peer connections can I establish at the same time on a machine of whose characteristics I know, and so on. If the X is the limit, is there anything I can do to improve that limit? Is there any bottleneck, and so on? And from what we've seen, the bottleneck is mostly not much in terms of CPU and memory and so on, because typically even the encryption part is not really that heavy, because most of that can also be leveraged using hardware encoding and stuff like this, but it's typically mostly in the bandwidth. So if transcoding is the neglectable part because you are not going to handle that yourself, that's usually the driving factor. And of course, whenever you use applications like Selenium and things like this to test, transcoding is an important aspect because it is always happening, at least an encoding part on the application itself, because even when you are using a fake device to capture something, you are still encoding media in the browser that you generate, which takes some resources and so on, which is what limits the number of concurrent sessions that you can simulate on a single machine, for instance.
Okay, thank you.
Thanks.
Other questions around? Okay, thank you, Lorenzo.
Thank you.